Everyone, hope you're all doing good. So in this video lecture we'll be learning about what are the factors that we need to consider while designing an optical fiber link, and in that comes the power budget analysis and the rise time analysis. So we'll be learning in detail each of these. So as you all know, the Lightwave system is of different types: point-to-point link, distribution network, and local area network. So each of these differ on their architecture and how their transmitter and receivers are connected. So in each of these architecture, the main design criteria that we have to look for is divided into two categories. It is primary design criteria and the secondary design criteria. So in primary design criteria, we have to take in account the bit rate and the link length. And as we have already discussed, the bit rate is associated with the dispersion and the link length is associated with attenuation. So when you are designing a optical fiber communication system, the primary design criteria or the primary categories that we need to look out for is bit rate and the link length. So, as already discussed, the primary design criteria is a bit rate and the length. So, how the bit rate is related to dispersion? So, you know what is dispersion? Dispersion is the change in the signal shape when it is being transmitted from the transmitter side to the receiver side. So, you have a square signal that is being transmitted to a transmitter. So, when it is at the receiver end, the square shape distorts, and it is at the receiver what the signal that we receive won't be in that square shape. Why that change in shape of the signal occurs is because of dispersion. So the dispersion factor limits the bandwidth. Okay, as we all know, the bandwidth is related to high frequency, and the frequency obviously depends upon the bit rate. So dispersion is related to bit rate. Okay, so the bit rate, because of the bit rate, when you are designing the system, we have to consider the bit rate. So considering the bit rate is considering dispersion. And the next factor is length. Okay, so what is link length? Link length, associated with link length is attenuation. Okay, what is attenuation? Attenuation is a process by which when a signal is being transmitted from the transmitter to a receiver, the intensity of the signal, the amplitude or the power of the signal reduces. And this reduction of the signal is dependent upon the link length. So as the transmission link length is the distance from the transmitter to receiver, as the link length increases, or link length is the spacing between the repeaters or the regenerators. So as the link length increases, the power or the amplitude of the signal reduces. So it relates to attenuation. So link length is associated with attenuation. And as I've already mentioned, when you're designing a system, we have to consider primary design factor. The primary design factor is bit rate and link length, and there are certain additional design categories also, or the secondary design factors that we have to consider. Those are the type of modulation, bit error rate, the signal to noise ratio, what are the cost of the components involved in our communication system, what is the upgradability and availability of these components that we are using in our optical communication system. So all these factors we have to consider when you are designing the optical link. So in the two primary design criteria, we have the bit rate as a calculation and the link length. So the link length calculation is known as the power budget analysis, and the bit rate calculation is known as the rise time budget analysis. So as you can see from the figure, there is a simplest point-to-point link communication system. You have an information source, you have an optical transmitter, you have an optical receiver, and you have a user, and these are connected with an optical fiber. This is the simplest form. So the second diagram you can see is an actual form of a communication system, where how the connections are being done. So the information source or the optical source from an LED or a laser is coupled through an optical fiber using fiber flight. From the fiber flight, we have connectors connecting the fiber, and from the fiber we have splicing. What is the process of splicing? When the information has to be transmitted a long distance, consider from Trivandrum to Delhi. So we cannot lay a single optical fiber. We have to lay multiple optical fibers, and connecting these multiple optical fibers is known as splicing. So in order to do the splicing, we have there is a loss associated with the splicing process. So the transmitter side and the receiver side are mirror images of each other. So whatever splicing you do in the transmitter side, the exactly the same you do on the receiver side, and similarly is the connector process. And at the receiver, you have a photo detector. Photo detector is the light from the optical fiber to the photodetector, and again coupled through a fiber flight. And the function of the photodetector is to convert the light into electrical energy. And this is how the actual connecting diagram of a point-to-point optical fiber communication link looks like. So now we have to determine what one of the primary important criteria is the length. Okay, and the finding of the link length is known as the power budget analysis. Okay, so what are the different factors that we need to consider in the power budget analysis that we'll see in the next slide. So the next topic is power budget analysis. So we all know that at the transmitter side we have the optical source. So this optical source is the primary agent which gives power for all the systems in the communication system. So the optical source is the major power source in the optical communication system. So at the transmitter side there is an analysis. There is a optical transmitting source of the power. The power at the transmitter is through the various connectors or the splicing is coupled through the channel optical fiber, and it and then it is received. So the power which is being transmitted at the transmitter is not necessary that it is same at the receiver. There can be reduction in power or intensity because of various losses that happens in the system. So in order that we have to analyze the power budget, we have to consider what are the losses that happens in the communication system. So as already mentioned, when you are using connectors in your communication system, there are losses in the communication. There in the losses of the signal at the connector side, at the splicing side, then so these all contributes to the power losses. So because of these losses, the power that we obtain at the transmitter need not be same at the receiver. And also when you are doing the power budget analysis, there can be various unseen factors which contribute to the losses, like you are laying your optical fiber under the road, and because at the different time different weighing vehicles pass. Some vehicles are carrying heavy goods, so it can weigh more. So because of that, there can be some bending. Because of that, there are some losses in optical fiber. So there can be very unseen losses. Because of that, we put a safety margin. We consider a safety margin loss when you're designing a system. Okay, that value is normally say, between 6 to 8 dB. That safety margin loss that we consider when designing a optical fiber communications system. So as you can see here, the losses due to the connector is given by alpha CON, and by the splicing is denoted by alpha splice, and there is an inherent loss in the optical fiber because of the attenuation that is given by alpha F. Now we'll see what is the equation of the power budget analysis in the coming slides. So when analyzing the optical power versus the bit rate, it has been found that at lower bit rate, the power of the source is much high, and we can transmit the signal at much higher distance at lower bit rate than at higher bit rate. So as the bit rate increases, the optical power intensity reduces. So at lower bit rate, we can transmit the signal at much higher distance than at the higher bit rate. So you are transmitting a signal with reduced bit rate, so this can propagate a long distance. So at the receiver, this signal will be affected by various losses in the communication system, like the connector loss, like the splicing loss, other unseen losses, then attenuation loss. So the received signal at the receiver will be suffering from all these losses, and the performance of the receiver is denoted by the factor sensitivity that we already discussed. The performance of the receiver is always denoted by the sensitivity. Okay, so in power budget analysis, you can see the equation, the total power PT, the total transmitted power PT is equal to PR. PR is the received power plus CL. CL is the total channel losses plus MS. MS is the system margin or the safety margin that I've already discussed. So the power transmitted and the power received are always expressed in dBm, and the total loss CL. The total loss CL is equal to this total loss is the total loss in the connector, in the splices, and the attenuation loss that we have already discussed. So the total loss CL is equal to alpha FL plus alpha connector plus alpha splice, and L is the link length. So here comes the link length, which is associated with attenuation. We have already discussed the relation between attenuation and the link length. So you can determine which all factors are required from this equation. Mainly the link length is what we extract from the power budget analysis. With this link length L, we can determine the spacing of the repeaters or regenerators or optical amplifiers. So this link length is an important design criteria when designing the link, when designing your optical fiber communication link. Okay, so with the power budget analysis, the link length can be obtained. So this is the equation, and as already mentioned, this safety margin is the unseen losses that happens in the system, considering that we consider a safety margin. And typically the total loss varies between 6 to 8, and PR and PT are the average power losses in the transmitter and the average power in the transmitter and the receiver. And safety margin, as already discussed, is a loss considering the component degradation and the unforeseen events. Okay.